Welcome to Maths Entry. Thanks for stopping by. If you find this helpful, please hit like and subscribe. Let's get started. Before we jump into the topic, we're gonna get a recap on significant figures, decimal places, and place values, because without that knowledge, we'll be unable to do the questions under upper and lower bounds. So let's jump into the recap. Significant figures. Rules for identifying significant figures. There are a few rules that you should know to identify what significant figures are. If you move on to this subtopic here, significant figures, under that the first number is 3875.0023. When start counting significant figures, you have to start counting from the very first digit of the number. So this is the first digit, 3, therefore we consider this one as the first significant figure. This 8 is the second significant figure, 7 is the third significant figure, so on. So you should know that non-zero digits are always significant figures. These are non-zero digits, therefore we consider them as significant figures. Next one, if you move on to the second number, it is 0.002358. You can see it here. So leading zeros, we call them leading zeros because it starts off with 0.002358. If you find leading zeros are considered as not significant figures. Therefore, the first significant figure of this number is 2. Second significant is 3. And third significant is 5. The leading zeros are not significant figures. If you move on to the third one, it is 0.00210300. There are leading zeros. You have to avoid them as counting significant figures. Therefore, the first significant figure here is 2, and second one is 1. Here, third significant figure is 0. Can you see the end zeros here? We call them trailing zeros. Trailing zeros are significant figures if the trailing zeros are in a decimal number. This is a decimal number. There are trailing zeros. Therefore, these ending zeros are considered as significant figure. So let's start counting significant figures. How many significant figures are there in this number? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 significant figures in this number. If you move on to the last one, 5800, it is a whole number. This is very confusing. This is ambiguous because there are trailing zeros, and sometimes we do consider them as significant figures, these ending zeros. Sometimes we do not consider them as significant figure. But if the number is a decimal number, we always consider them as significant figures. Next, decimal places. I think it is so easy, decimal places, to be start counting right after the decimal point. So decimal point here is here, then the first decimal place is 0 of this number, 0.001. First decimal place is 0, second decimal place is 0, third decimal place is also 1. Next one, 58.356. Then here the first decimal place is right after the decimal point, which is 3. In this case, 0.0023. The first decimal point becomes as 0. No matter whether you are getting leading zeros or not, still if we are getting anything right after the decimal point, we do count it as a decimal point, decimal place. That is all about decimal places. Place values. Place values refer to the value of each digit in a number. Let's say how to find out place values of any number, any digit in a number. Now there's a number, and you see it is 385,691.012023. It's kind of a large number. Let's see how to get the place value of each digit in this number. I will write a number here. Check out whether you can identify the place value of each digit, something smaller number I will write here. Let's get 321. In this case, the 1 applies in the position of units. And this one is tens position, and this one is hundreds position. In this case, if you will see this type of number, you have to figure out where units lies, where tens lies, and hundreds, so on. This is a mixed number. Can you see this part? This part, we know that it is a whole number part. This part is the decimal number part. When we get this combined number with whole number and decimal number, you need to identify where the units position is. Right before the decimal point, this number 1 here, the digit 1, it is the unit position. Therefore, the place value of this one is units or ones. Next one is 9. It is then tens. Place value is 10. This is 100. The place value of 6 is 100. The place value of 5 is 1000. The place value of 8 is 10,000. The place value of 3 is 100,000. And we are done with the whole number part. We move on to this first decimal place. Here, right after the decimal point, this decimal place, the place value of the first decimal place is 0.1. The place value of the second decimal place is 0.01. Second decimal place, therefore, can you see there are two decimal places? The place value of this one is 0.01. Next one is 0.001, 0.0001 is the next one. We have to increase the zeros as much as you are getting the decimal places. When we think about the place value of a decimal number, it is a bit different. So this is the number with decimal parts as well. If I ask you to get place value of the third significant figure, so you have to start counting the third significant figure from the first digit of this number. 1, 2, 3, this is the third significant figure. Then the place value of this one is 1000. Let's get the place value of the 10th significant figure. Then you have to figure out where the 10th significant figure lies. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the 10th significant figure. Then the place value of the 10th significant figure is the 0.0001 because it is the 1, 2, 3, 4, 4th decimal place. That's how we have to deal with place values, significant figures, and decimal places all together. For the next questions, you have to work with these decimal places, significant figures, and place values. Let's start off with the straightforward questions. To begin the straightforward questions, before doing anything else, you have to identify the keywords of the upper and lower bounds. Let's say that you are getting a question. Write down the lower and upper bound for each measurement to the given degree of accuracy. First keyword is round to, second one is correct to, nearest to, or to, just to. Once you identify what the keyword is, you have to go to the question. Again, check out whether one of the keywords is given and underline that keyword. Let's underline this keyword to the nearest unit. Once we underline the keyword, we have to create the key point. Here, nearest unit, this is the way how we create the key point. Key point is what you need to get key point. Key point comes in this way. You have to get the place value of this nearest thing. Nearest, you have to read it in this way, to the nearest what. Now in this gets unit, then the place value of unit is 1. Once you get the place value, Always you have to get the place value. Now in this case, nearest unit place value is 1. You have to divide it by 2. Then the key point becomes as 0.5. This is the way how we get that key point. Let's say it is correct to unit, then still it is unit. The place value of unit is 1, then 1 should be divided by 2. If it is nearest to unit, still it is unit, then you have to get the place value of unit, which is 1, and divide by 2, and it is 0.5. Now once we get the key point, it is easy to get the upper bound, lower bound of this basic questions. Let's get the upper bound of 6 first. So upper bound of 6 is 6 plus this key point. It is 6.5. Lower bound of 6 is 6 minus 0.5, which is 5.5. Next one, 17. Still the key point is 0.5 because it is all these three measurements are rounded to or corrected to unit, nearest unit, therefore it is 0.5. Then this one upper bound is 17 plus 0.5, which is 17.5. And lower bound becomes as 17 minus 0.5, which is 16.5. Remember, always you have to figure out what the key point is. Key point is the so important one. If you know what the key point is, you can get the upper bound, lower bound of any question. To get the keyword key point, you have to underline the keyword first. So nearest what, then get that what thing and get the place value always. In this case, the what thing is unit. So we are getting the unit, which is 1, and we divide it by 2, which is 0.5. After that, we have to add that much to the original measurement. To get the upper bound, you have to subtract that key point to get the lower bound of the original measurement. That's the first question. Let's move on to the second question. The second question says 740, 700 to one significant figure. Now this is different. One significant figure. It is the type 2. One significant figure. Let's move on to the first measurement. First measurement is 7. So let's underline the keyword to one significant figure. Then you have to go to the first significant figure of the measurement. This is 7. Then the first significant figure is 7. After that, you have to get the place value of this correct to or rounded to 1, which is you have to get the place value of the first significant figure. We are coming to the first significant figure. We are getting the place value of it. The 7 lies in the position of unit. Therefore, I have to get the place value as 1. In this case also it is 1. 1 should be divided by 2. We always divide the place value by 2. To get the key point, it is again 0.5. Now to get the upper bound of 7. Upper bound of 7, I have to add 0.5. 7 plus 0.5. Which is 7.5. To get the lower bound, I have to subtract this much from the measurement, then it becomes 6.5. That's how we get upper bound and lower bound of 7. Let's move on to the second one, which is 40. In this case, what is the place value? What is this first significant figure of 40? The first significant figure of 40 is 4. The place value of 4 is 10. Then 10 should be divided by 2. It becomes as 5. This time our key point is 5. Then when getting the upper bound, we have to add this much to the original measurement, which is 40 plus 5, which becomes as 45. Then my upper bound for 40 is 45. When getting lower bound, I have to subtract this much from the original measurement. Then 40 minus 5, which becomes 35. So let's move on to the third part, which is 700. 700, the first significant figure of the 700 is 7. Therefore, its place value is 100. Then I have to divide 100 by 2, which becomes 50. This time our key point is 50. Then when getting upper bound, I have to add 50 to 700, then it becomes 750. When getting lower bound, I have to subtract this much from 700, it becomes 650. This is the way how we apply upper bound and lower bound for the basic question. Let's see how to do this question. There are two questions that are a bit different but basic. 2.5, 14.5, 146.0 to the nearest 0.5. Did you notice here there is no any specific keyword like correct to, significant figure, decimal place, to the whole number, or 1 centimeter or kilometer? There's nothing like that. This is under the fourth type of the key point, special case. Special case, it explains nearest value. In our case, it is to the nearest 0.5. If you don't have nearest significant figure, nearest decimal place, or nearest kilometer, nothing, you have to get the value as it is to get the key point. So let's create the key point. 0.5 divide by 2, because we don't have here any significant figure or decimal place or whole number, nothing here. Then we get the value. To check whether there is visible here, then if there's there, it means that you need to get the value as it is, because there's no significant figure, no decimal place, no kilometer. So we got this one as it is. Once we divide it by 2, we are getting 0.25. Now this is our key point. So let's get the first measurement. For the first measurement is 2.5. So if I want to get the upper bound, I have to add 0.25. Then it becomes as 2.75. Next one is low bound. If I want to get the low bound of 2.5, it's to 2.5 minus 0.25. Then it becomes 2.25. That's how we do when it is just to the nearest. Since there plays a major role here, because it is the one that explains we have to get the point or the value as it is. Next measurement is 14.5. 14.5. Second measurement is 14.5. And let's get upper bound. 14.5. We have to add 0.25, the same key point for each and every question here in the third question. Then it becomes as 14.75. Low bound, it is 14.5 minus 0.25. Then it is 14.25. Third question, third part, it is 146.0. Again upper bound. 6.0 plus 0.25, which is 146.25. Low bound, 146.0 minus 0.25. Then it becomes 145.75. Let's see how to do this question. The key point, underline the keyword. In this case, it is to the nearest 0.5. If we move on to the fourth question, the key point keyword is to the nearest 10. No significant figure, again no decimal place, no kilometers, no centimeters. Then get the value as it is. This is under special case. So 10, I'm dividing it by 2. It is 5. The first measurement is 50. If we want to get the upper bound, 50 plus 5, which becomes 55. If we want to get the lower bound, 50 minus 5, which is 45. Let's do one more question, which is 230. If we want to get upper bound, 230 plus 5, it is 235. Then if we want to get lower bound, if you want to get the lower bound, 230 minus 5, which becomes as 225. That's how we apply the key point of the special case when we don't have significant figures, decimal places, centimeters, kilometers, nothing but just a value. This is the way how we do it. Let's do this question. This is also under the same key point, which is under special case. I'm reading out the question: 0.2, 7.6, 12.4 to the nearest 0.2 of a unit. You have to underline the keyword. What is the keyword? To the nearest 0.2. There is no any significant figure, no decimal point, no decimal place, no kilometers, nothing, just 0.2 of a unit. Then you gotta get this one, 0.2. Whenever we have this type of one, we do not get the place value. Rather than place value, we are picking the point or the value as it is, because there is no significant figure, there is no decimal place, no kilometers, nothing. The nearest value, the nearest value. This is under this special case again. So 0.2 to be divided by 2, which becomes as 0.1. After that, let's get the upper bound of 0.2. So upper bound of 0.2 can be taken as 0.2 plus 0.1, which becomes as 0.3. Low bound of 0.2 can be taken as 0.2 minus 0.1 equals 0.1 again. Upper bound of 7.6 plus 0.1, 7.7, and low bound of 7.6. We have to subtract, then it becomes as 7.5, same way to 8.4. Let's move on to the other question. It is a bit different. We didn't do this question yet. Sixth question, 0.34, 7.23, 12.89 to 2 decimal places. Now decimal places has come here, therefore underline the key word, which is to the 2 decimal places. What's the place value of the second decimal place? The place value of the second decimal place is 0.01. We did this one. I have to divide this one by 2. Always get the place value and divide it by 2. If it is decimal place, significant figure, or any centimeters, kilometers, you have to get the decimal place and divide it by 2. So once we divide this one by 2, the key point becomes as 0.005. If you want, you can plug in the values into the calculator and check it out. Then the calculator will give it is as 0.005. Now let's get the upper bound of 0.34. So 0.34 upper bound becomes as, I have to add this much 0.005, which becomes as 0.345. And low bound becomes as, I need to subtract this much 0.005. Let's subtract, then how much do you get? 0.335. What about this one? 7.23. Upper bound of 7.23. We gotta add this key point, which is 0.005 again. Then it becomes 7.235. Low bound becomes as 7.23. Subtract 0.005, which becomes as 7.225. That's how we are getting when it comes to decimal point. Okay guys, check this out. Check out whether we can do this one. This is I'm reading out the question. A sheep is weighed by a farmer as 43 kg to the nearest kg. What are the lower and upper bound weights for the sheep? You have to identify what the keyword is. Let's read out again to get what the keyword is. A sheep is weighed by a farmer as 43 kg to the nearest kg. So you could underline to the nearest kg. Now this is your keyword. In this keyword, we have only one unit as kg, but there is no any number before kg. You don't have a digit there. You don't have a number. When you get just the kg or unit or centimeters, kilograms, kilometers, you realize that there is one invisible one in front of kg. So if you don't see it, just write it. 1 kg. Then you can read it out as this way. A sheep is weighed by a farmer as 43 kg to the nearest 1 kilogram. 1 is normally not written in the question, but we should know that it is 1 kg. It is measured to the nearest kg, 1 kg. Then let's get 1 divided by 2. It becomes 0.5. 0.5. Then the upper bound becomes as 43 plus 0.5. which becomes as 43.5. Low bound becomes as 43 minus 0.5, which becomes as 42.5. That's how we do whenever we are getting questions under kilograms, kilometers, meters, centimeters. Remember, there are 1b1, it won't be written there. You should know that there is invisible one knowledge. Then pick that one and divide it by 2 and get the key point and do the question. When we have to deal with limits of accuracy, you should know that how to write it as an inequality. Limits of accuracy means you have to deal with upper and lower bounds. Underline the keyword nearest centimeter. Nearest centimeter means I have to get key point, which is 0.5. The nearest centimeter, the length L of a stapler is 12 centimeter. As an inequality, we can write it as 11.5. L is the length of the stapler is greater than or equals 11.5. Smaller than 12.5. Let's say that for part A to J you are given a measurement. Write the possible values using an inequality as above. It means this is limits of accuracy or upper and lower bound. Using it upper and lower bound, you have to create an inequality. We call it limits of accuracy. This is now in this case the first measurement is measured to the second significant figure. This is our keyword. Second significant figure. Second significant is 7. It lies in the unit position. Therefore, I have to get 1. 1 should be divided by 2. Again, our key point is 0.5. Then to get the upper bound, add this much to the original measurement, which becomes 17.5. Next, to get the lower bound, I have to subtract this much from. Then it becomes 16.5. Now we got to leave our answer as an inequality. Start off with the lower bound. Lower bound is 16.5. And the mass should be greater than or equals to this lower bound. Or else this side we write lower bound. After that, smaller than but not equals to the upper bound, which is 17.5. So this is upper bound. That's how we do it. This is final answer, limits of accuracy. Then in this case, it is measured to the third significant figure, D 256 kilometers. to the third significant figure. The third significant figure lies 1, 2, 3. It is again units position, which is 1, then divide by 2, then 0.5. Then again you have to get upper bound. Upper bound becomes 256.5. Because we got to add this much to the upper bound. Low bound, we need to subtract this much from the measurement. It is 255.5. Then you have to write the limits of accuracy as an inequality. First start off with the lower bound, which is 255.5. And distance should be greater than or equals to this lower bound, the side that is lower bound, and smaller than to the upper bound, which is 256.5. The meaning of this one is this measurement can be anywhere in between these two, but you have to exclude this measurement. Anywhere in between these two, including this, excluding this. In this section, I'm going to cover upper and low bounds of compound measurements. Let's move on to this one. These two keywords here. Whenever you see these two keywords in a question, here, maximum or minimum. Maximum means the word itself explains upper bound. Minimum means lower bound. Here the maximum value of A plus B. Now this is an expression of compound measurements. There is more than one measurement, therefore it is compound measurement. If you need to get the maximum value of A plus B maximum value, then we know that maximum can be interpreted as upper bound. Then A plus B, we have to get upper bound. This is addition, upper bound, and this is an expression. Whenever you are asked to get the upper bound of an addition, don't add the two values and get the upper bound. That is not the way that we have to get. We have to get the maximum possible value for A plus B. If you add these two and get the upper bound, that will be something less than the original upper bound of A plus B. Therefore, if it is A plus B and you get upper bound, apply upper bound for A individually or separately and plus get the upper bound of B. It is easy if it is addition, always the same thing to be applied. Upper bound, upper bound. It is obvious we have to get the maximum possible answer for this one. Then this one has to be the biggest one. This one has to be the biggest one. Therefore, we have to get biggest and add them together. Then it will be enormous. This one, it is minimum, same way. If the term comes minimum, then we know that it is low bound. This is low bound. Then A plus B. Again, it is addition, but this time we need to get a minimum answer. Same way, if it is a compound measurement, never get the answer for A plus B and then apply low bound. It is not the way that we have to do. We gotta do individual, we gotta apply low bound. If it is the minimum possible one, A, low bound, plus B, low bound. That's how we get this one. If it is addition, low bound. If it is addition of upper bound. Same thing to be applied for addition, multiplication. It is maximum, therefore we need to get upper bound of the multiplication. AB means if it is multiplication. In algebra there is a hidden multiplication sign, so I separated it with multiplication, then it's easy to understand. If it is multiplication, the upper bound should be applied again individually, the maximum possible answer for A into B. So therefore, we have to apply upper bound individually. Do not multiply and apply upper bound. You have to get them individually unmultiplied. Maximum possible answer, upper bound of A, upper bound of B. Let's say that you need to get the minimum. Then again, split it in this way, A into B, minimum means lower bound. Same way, A lower bound into B lower bound. Addition and multiplication is easy. If the question says to get the upper bound or lower bound, apply individually same thing, upper bound, or if it is low bound, low bound, low bound. Multiplication also same way. If it is multiplication, you need to get the upper bound of that multiplication, then apply it individually. A upper bound, B upper bound, same way low bound, A low bound, B low bound. When it comes to subtraction, it's a bit different and it's a bit complicated. So let's write maximum of A minus B, then maximum minor, then maximum possible answer should be upper bound. If it is a subtraction, we need to get the maximum possible of the subtraction. If the question says A minus B upper bound, then if it is a subtraction, always start off with the upper bound of A and lower bound of B. So you have to change them. If the final answer has to be maximum, which is upper bound, then the starting measurement has to be upper bound, and then second one has to be lower bound. You have to change them if it is a subtraction. The minimum value of A minus B. Minimum again, minimum means low bound. Then A minus B, low bound, the smallest possible answer. So we have to start off with low bound of A, because low bound should be the final answer. Then A lower bound minus B upper bound. Here, this one should be applied always for the first measurement. Next one should be the other way around, division. When it comes to division, it is maximum again. Then A over B, we know that we have to get maximum. Maximum means upper bound. Then we have to get upper bound of A, lower bound of B. For division and subtraction, always we apply the different accuracy measurements. It means if you're starting off with upper bound, the numerator has to be upper bound, then the denominator has to be lower bound. If it is A over B, lower bound, then the final answer has to be lower bound. Then you gotta start off with the lower bound of the numerator. Then denominator would be upper bound. That's how we apply this division and subtraction. Next, when you're getting a formula like this, it is also under compound measurements. There is a fraction, algebraic fraction. Let's say that in this whole of this one, we need to get the upper bound. The final answer has to be upper bound. So how do we work out with this one? This is a fraction, algebraic fraction. So if it is fraction B, then for A minus B, the whole expression A minus B should be upper bound, because this is a division, over A plus B, it has to be lower bound. Division, when it comes to division, the numerator has to be the upper bound and the denominator has to be lower bound. Always to the numerator we have to apply the final accuracy, what you're asked to get to the numerator. It means upper bound to the numerator, lower bound to the denominator, always different from this one. And you are having here expression, therefore you have to apply it separately. Then A should be upper bound, this is subtraction, and minus B should be lower bound. A here, lower bound, because this is addition. Addition we do not change, it is same thing. B has to be also lower bound. That's it. Then if you are having any values of a's and b's, you have to get the upper bound of a and apply here, lower bound of b and apply here. Likewise, you need to get the final answer. Let's move on to the past prep questions. In this case, p equals a brackets c plus y. A equals 8.3, correct to two significant figures. C equals 2, correct to one significant figure. Y equals 15, correct to the nearest 5. Work out the upper bound for the value of p, show you working clearly. Very first thing is, identify the keyword and underline it. In this case, correct to two significant figures. Two significant figures, you have to figure out what the second significant figure of a, which is 8.3. In this case, second significant figure is this digit 3. It lies in the first decimal place. Therefore, you have to get 0.1 divided by 2, which becomes 0.05. So this is our keyword for a, key point for a. C equals 2, correct to one significant figure. The first significant figure is 2. It lies in the position of units. Therefore, you have to pick 1 to be divided by 2, which becomes as 0.5. Our key point becomes 0.5 for C. Third one, y equals 15, correct to the nearest 5. Can you remember this is the fourth special case? Consider and get 5 and straight away divide it by 2, which becomes 2.5. Now this is, we need to get upper bound. So let's write the equation as it is. P equals a times bracket c plus y. We gotta get upper bound. Upper bound, can you remember that this is a multiplication? A times a multiply. If it is multiplication, we have to apply individually. Upper bound, then a to be written as upper bound. C plus y to be written as upper bound, the whole case to be taken as upper bound. Here c plus y, it is inside bracket and it behaves as an one expression. Therefore, you need to individually again to get the upper bound of whole of c plus y. We gotta apply upper bound for c, upper bound for y individually, separately. Let's write it in this way. A times upper bound, open brackets, c upper bound plus y upper bound, close the bracket. Now let's get the upper bound. It's better to write in the question. If you write everything you need separately, you are getting additional marks. So upper bound of a, which becomes as 8.3 plus 0.05. Upper bound of c, we are getting 2 plus 0.5. In this case, we are getting here 8.35. Here we are getting 2.5. And upper bound of y, we are getting y, it is 15 plus 2.5, which becomes 17.5. Then, let's apply the values. So 8.35 into c upper bound, which is 2.5, plus 17.5. Then 8.35 into, once we add these two, we are getting 20. The answer becomes as 167. This is the final answer. So you are getting marks. If you get 8.25, 8.35, 2.5, 1.5, 17.5, 12.5, you are getting 1 mark. After that, for application of this one, you are getting 1 mark. So basically, 1 mark, unconditional accuracy mark here, and here you are getting want method mark. And here you are getting answer mark. That's how we are